Alright, let's go ahead and get started with Lesson 4, Experimental Error, Part 2 of Lesson 4. So we're going to look at experimental error in this lecture video. Experimental error is always going to occur in a lab. You're going to do a lot of labs this year, and you're going to have errors that are going to occur. That's going to affect your reliability of your final results. I'm going to highlight a few things here. So first of all, you're always going to have experimental error. Oops, I don't want to use red. Let's use a highlighter. You're always going to have experimental errors and uncertainties in an experiment. And the magnitude is going to affect the reliability of the final results of your experiment. What you need to be able to do is become comfortable with identifying, analyzing, and evaluating experimental error. A big part of your lab report will consist of evaluating sources of experimental error and how to avoid these errors in the future. Alright, so we're going to look at our first type of experimental error. This is known as random error. Random error, by definition, is basically this. It arises mostly from limitations in the instrument's precision and can lead to readings being above or below the true value. Note, random error will always occur for any measurement. This is because the last digit of any measurement is estimated. So in a long sense, or summarize this idea, random error exists because there's always one digit estimated in any measurement. Our instrument has a problem in its precision. It's only as good as that last estimated digit. Alright, and so that's where the random error is going to occur, is in the last digit of any measurement. Alright, so what causes random error? Again, limitations in a measuring instrument's precision, the estimation of that last digit. All I can say is that because we have to estimate the last digit in a measurement, we have random error automatically. Alright, what else causes random error? Well, essentially changes in the surrounding environment during an experiment, such as temperature variations or air currents, can cause a change or an increase in random error. How do we reduce random error? Well, simply this. We need to use a more precise instrument, one that we can record more decimal points, more decimal point places out. That will help to reduce it. Repeating an experiment a lot of times, 3 to 5 times is what's recommended, and then averaging those results. By repeating an experiment multiple times, that really does help reduce the random error. So we're going to expect you to do that in your labs. Alright, again, it is always important to remember that random error can never be eliminated. Basically, again, is because you're always going to have one uncertain or one estimated digit. Alright, so how do we determine the random error? How do we determine how much random error there is in a measurement? Alright, now obviously the last digit, because it's estimated, that's where our random error occurs. So we have to look at that last digit. Alright? And then from that last digit, we can kind of determine how much random error there is associated with that instrument. So we have two types of measuring devices, a digital scale and an analog scale. Digital, you're familiar with. You know what digital is. This age, everyone uses everything digital. Okay? But some things in our class are going to be analog. Those are not digital equipment. Okay? And so we need to learn how to determine the random error from both. So if you have a digital scale, you're going to record the random error as a plus or minus value of the smallest scale division. I'll show you how to do that in a minute. If you have an analog piece of equipment, then you're going to determine the random error by taking a plus or minus value of half. That's 1/2 the smallest hash mark. And I'll show you how to do that as well. So write these two down, these two criteria for determining a random error, and then we'll get down to business here. So here we got a digital balance. All right. You can see from this balance that it's making a reading of 0.015 ounces. So I'm going to actually write that down. 0.015 ounces. All right. Now, how many sig figs do we have in this measurement? All right. The answer is 2. All right. 2 sig figs. All right. The 1 and the 5. Remember that the 2 zeros are not significant. They are just placeholders because they come at the beginning of the measurement. All right. So which digit is being estimated? That's right, the 5. It's my last digit. So the balance itself, even though it's digital, the balance itself is estimating that last digit. All right? It's estimating it right now as a 5. All right? So because it's estimating the 5, that is the digit that has the random error. So how do we determine the random error range? Well, we're going to put it as a plus or minus range value. And since there's 3 decimal points, my error is going to be 0.001. All right? We're always going to have a plus or minus all the decimal points of 0 or 0.00 and then 1 at the very end to identify the range. So this 5 can actually be a 6, or it could be 1 down, and it could be a 4. And so that's my estimated random error. Anywhere within that range it could exist. All right, here's another digital balance. This digital balance is going to read 9.30. So 9.30. We'll say grams. How many significant figures? There's 3. That 0 is significant. The last 0 is my estimated digit. And the balance again is estimating that value at 0. Another time you put that on there, it could be estimating that maybe 9.31. Okay? Just depends on the balance. But the idea is that 0 is estimated, therefore has random error. So we have to address that random error as a plus or minus value. This time we only have 2 decimal points, so it's 0.01. Alright? Because of the 2 decimal points. Notice that the last decimal point is in the same place value as my 0 or my estimated digit. Alright? So that's how you deal with digital equipment. Most of the time with digital equipment, we actually give you the plus or minus value, the random error, what it is. And so I'll usually give you that as we do a lab or experiment. Alright, so let's turn our attention to analog. Analog is a little bit tougher than digital to determine. Alright, so we have 3 analog measuring devices here for volume. The first one is a beaker, then a graduated cylinder, and then a burette. So let's go ahead and look at the magnitude of the volume in the beaker. If you look closely, you would know that you have hash marks that are going up by tens, it looks like. So we got 10, 20, and 30. In fact is that's the smallest hash mark. So all we know for certain is the 2, basically. We know that it's definitely 2, and then we can estimate that the 2 is in the 10 spot, so we can estimate the last digit in the 1s to be probably 28 is what I'm going to estimate. Again, that's my estimated digit, 28 milliliters. Okay, and then we need an uncertainty, plus or minus range. Well, since my 8 is my uncertain digit, for an analog piece of equipment, you're going to take the smallest hash mark and divide it in half. Well, the smallest hash mark is going up by tens. Alright, since it's going up by tens, 10, 20, 30, we're going to take half of that. So half of 10 is 5. So that means my random error is going to be plus or minus 5. Alright, so it can my answer is 28 plus or minus 5 milliliters. So it's 5 up from 28 or 5 down from 28. Alright, now let's take a look at the graduated cylinder. Okay, the graduated cylinder should give me a little bit more precision. It's a better instrument. Alright, so I should be able to record more digits with the graduated cylinder. So let's look at what we're going up by. It looks like we're almost going up by ones. So we have 27, 28, 29, and then 30. Okay, so we're going up by ones here. So what I do know then is the 28. That's a for certain thing. So I'm going to go ahead and write 28 here. Milliliters, plus or minus. Now, since my smallest hash mark is going up by ones, what's half of 1? 0.5, exactly. So that tells us that, oh, actually, I didn't do my estimated digit. I jumped the gun. Alright, I have to estimate one digit here. So I know for certain by 28, but I can estimate my last digit to be a decimal point. So 28.1 is what I'm going to estimate it as. See if you get similar to that. Again, doesn't have to be exactly right on because that last digit is estimated. So 28.1 plus or minus. Okay, again, now since the smallest hash mark is going up by ones, the half of 1 is 0.5. So that means that my uncertainty or my random error is 0.5. Alright? So as you can see here, using a graduated cylinder, what happened to the random error compared to the beaker? My random error in the beaker was plus or minus 5, and then for the graduated cylinder, it's plus or minus 0.5. So the graduated cylinder is more precise, and therefore it has less random error. What about a burette? Well, a burette should even be more precise than the other two. It should give us more decimal points. And indeed it does. If you look at it, we're going up 28 and then 29. Those are big hash marks, but we have some small ones in between. So we have 28.1, 0.2, 0.3, 0.4, and so forth. So I'm going to say my value is 28. I definitely know that because of these small hash marks, it's 0.1, 0.2, 0.3. So 28.3. And then I'm going to estimate my last digit to be 1. So 28.31 is going to be my measurement with the 1 there as my estimated digit. Alright, see if you get somewhat similar to that. So what is my random error, my plus or minus? Well, since my smallest hash mark is going up by 0.1, alright, you can see that, smallest hash mark, again, these are all going up by, if I can mark on that, 0.1s, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1. So again, there are that smallest hash mark there going up by 0.1. So what is half of 0.1? It should be 0.05. So my random error should be 0.05 milliliters. Right? So is that even better than the graduated cylinder? Actually, yes. So my random error is decreasing. It's going from plus or minus 5 for the beaker to plus or minus 0.5 for the graduated cylinder, and then finally for the burette it's plus or minus 0.05. Alright, so if I was measuring volume, which of these three instruments would be the best to give you the best precision or to reduce the random error? And if you said the Briere, you would be right on. And that's what I would choose. Alright, so that's how you determine the value of random error. Remember that random error always occurs because the last digit of every measurement is estimated. And so therefore, the random error is going to be expressed as a plus or minus value. Alright? So we'll practice this in class so you get more familiar with it. I know it's difficult for the first time through. Alright, we're going to look at systematic error. This is the last error we're going to look at. Systematic error, we're going to have to spend a lot of time throughout the year recognizing. It takes time to learn about systematic error. Alright? So we're just going to kind of introduce it to you now. So by definition, systematic error are errors that affect the accuracy or the true value of the experiment. Alright? So in other words, systematic error is going to deviate from the true value or our real value. Alright? How does systematic error occur? What are the causes? Well, the biggest thing is poor experimental design or procedure. If you design a bad experiment, you're going to get a load of systematic error. Alright? So don't do it. Flaws or defects in instruments will cause systematic errors. So if our instrument isn't running correctly, we'll get systematic error, which will affect our accuracy. How do we reduce systematic error so that we can get better accuracy? Well, making careful experiments, designing them carefully in a careful procedure, using really good instruments, the best instruments you possibly can, and make sure that those instruments have been calibrated correctly. All of these things, if we do, we can reduce the random error and get a better or more accurate result. And the more accurate your final result is, and in other words, how close it is to the true value, the better your lab report score is going to be. Alright, so you have to learn to recognize what is causing the systematic error in your lab report. What's causing it? This isn't easy. It takes some time and practice to learn. Alright, here are some examples. Now I don't expect you to write down these examples or memorize them right now. Just have an idea that there are different things in an experiment that can cause systematic error. So for instance, if you're measuring the volume of water from the top of a meniscus rather than the bottom, this is going to lead to volumes which are too high. It's going to create an accuracy problem. If you overshoot the volume of a liquid delivered in a titration, this is going to lead to volumes which are also too high. Affects the accuracy. Using an acid-base indicator whose endpoint does not correspond to the equivalence point of a titration. Affects the accuracy. Again, some of you may know what a titration is and so forth. Not a big deal. When you lose too much heat, when you're trying to measure the temperature, but you're losing so much heat through an exothermic reaction, so you can't get a very good accurate temperature because you're losing heat. This would cause you to have an accuracy issue or a problem. Alright, so these are just a few examples, and as we go through labs throughout the year, we'll help you to point out where the systematic error is, and help you to evaluate that and to think about possible ways and how to reduce that systematic error. Alright, now, can we put a numerical value to systematic error? The answer is yes. Alright, we do so by using what is called percent error. Alright, percent error is a quantity, a percentage quantity, that tells us how far away we are from our true value. Here's the equation. It's a simple equation, one you should learn or memorize so that you can perform this or use this equation in your lab reports or tests or homework or so forth. Simply this. You take your experimental value. That's the value that you actually determined during your lab. And you subtract that value from the accepted or true value. And then you're going to divide that by the true value or accepted value and multiply it by 100 to give you into a percentage. The percent error, whatever that percentage is, tells you how far away you are from the true value. The higher the percentage, the further you are from the true value. What we would like to do as a goal, as an individual student, is to have a percent error of 5 or less. So 5% or less is our target goal. If you can do an experiment and have your systematic error down to 5% or less, you're doing really well. You're doing fantastic. You're using good equipment, your procedure as well, and you're following your procedure and experimental design very closely. All right. So these are all important ideas. All right. Also, to make note is often we use an experimental value as an average. All right. This is what I prefer you to do in most cases. Is when you have multiple trials. Remember, to reduce random error, we want to have 3 to 5 trials, and so we'll average that data set together, and so we'll take the average value and find the percent error using that average value. Sometimes we can use single values to do that, but average is what we're going to choose. Also, the percent error can be negative or positive, and the direction of error, so in other words being negative or positive, is going to tell us a lot about our systematic error. And so I'll help you with that too, and help you to understand what the sign means in terms of our systematic error as we get into more experiments and so forth. All right, so this is it for this lecture video. I would suggest that you study this lecture video very closely. It's very important, the information that we're learning here. If you need to re-listen to this multiple times, take better notes, study those notes, do so. We will practice random and systematic error throughout the year. We will look at it in class next time as well, and get you squared away. All right? So that is it for now.